Hey guys, this is Mrs. Donaldson, and this is going to be your lesson for your 16B pH calculations. So go ahead and make sure you have your 16B notes out, as well as a calculator. And I'm going to give you a heads up that me working with this little stylus has been interesting, so if you can't read anything, you know where the notes are posted in the room. So all I have to say, yesterday we finished talking about the theories of acids and bases. And Arrhenius said that a compound that's acidic will dissociate in water and produce hydrogen ions. So if you have a beaker full of lots and lots of hydrogen ions, we could classify this solution as acidic. If you had a beaker full of hydroxide ions, Arrhenius said this would be a base, or it'd be very basic. And so today we're going to quantify this, of not just saying, oh, this is really acidic or this is really basic, but we're going to put a number to this has a concentration of 1 times 10 to the negative 6th, and this is 1 times 10 to the negative 8th. And then we're going to get sick of those exponents, and we're going to drop them down and be like, hey, this has a pH of 6, or this has a pH of 8. So we're going to be actually quantifying how acidic or how basic our solutions are. So right off the bat, if we want to know the concentration of hydrogen or hydroxide, one way is if they give us the molarity of the acid or the base. And the first thing you'll want to do is see how the acid or base dissociates or ionizes. So in this example, hydrochloric acid splits up into its ions. Everything is balanced 1 to 1. Barium hydroxide would break up into barium ions +2 because it's in group 2, and OH -1 from the back of your periodic table. However, I have 2 OH groups, so I'm going to need to keep that thing balanced. So when we actually want to know the concentration of the hydrogen ions, we know that the acid had a concentration of 1.5. Well, in this case, because there was only one H, then we're going to say that these two things are equal. So the hydrogen concentration is also 1.5. But for number 2, our basic solution had a molarity of 0.4. But when this base dissociated, we have the double amount of hydroxide ions. So we're simply going to just double our molarity. So the concentration of hydroxide would be 2 times 0.4 molarity, giving us a concentration of 0.8. So the trick is multiply, wow, I can't spell. Let's try it again. Multiply the molarity of the acid or base with the number of hydrogens or hydroxides in the formula. So we wrote out the dissociation, but like another way is if we look at barium hydroxide, there were 2 hydroxides. So without having to actually write out the dissociation, we would have, by looking at the formula, there's 2 hydroxides, so we would double that concentration. HCl, there's only one H, and so that concentration is equal. But if it would have been like H2S, hydrosulfuric acid, we would have doubled our concentration. So in order for an acid and base to ionize or dissociate, it has to be placed into water. Well, something that we need to remember about water is that water can also dissociate into hydrogen and hydroxide concentrations, but they will always be equal. And so if we had to write that out, water dissociates into hydrogen ions and hydroxide ions, and we'll put their state of matter, which is aqueous. So water is neutral at 25 degrees Celsius, and it has been found that the concentrations of hydrogen and hydroxide have been found to be 1 times 10 to the negative 7th molarity. And so if we apply that with what we know about equilibrium from last unit, kinetics, products over reactants, if we wrote an equilibrium expression, we would cross out all of our solids and liquids, and so we would, in this case, just have products. It would be our hydrogen concentration times our hydroxide concentration, and if we plugged in our equilibrium concentrations, 1 times 10 to the negative 7th times 1 times 10 to the negative 7th, we would multiply these in the calculator, and you can do this a couple different ways. When you do times 10, remember you can substitute that in for E using that second comma button. Or mathematically, when we multiply these two things with exponents, we can actually add up our exponents and get 1 times 10 to the negative 14th. This would be our equilibrium constant. So something we're going to start talking about is, and I'll switch colors, is the concentration of hydrogen compared to the concentration of hydroxide. And we're working with really small numbers, and so those can be kind of confusing. So something we have to remember is if I have 1 times 10 to the negative 5th molarity versus 1 times 10 to the negative 9th, which number is bigger? Well, this number is bigger, because when we're dealing with negative exponents, this is how many times the number is being divided by 0. It's our decimal number, 1, 2, 3, 4, 5, compared to, this was divided 9 times by 10, so it would be 1, 2, 3, 4, 5, 6, 7, 8, 9. And so this is actually our bigger number, and so if we have a beaker that has way more hydrogen, we would say this is an acidic solution because it has a higher concentration of hydrogen ions than hydroxide ions. So keep that in mind as we work through these fill in the blanks. So if we have an acidic solution, so we add acid to a solution, we're going to have a higher amount of hydrogen ions. Therefore, the amount of our hydroxide ions will have decreased. And the hydrogen concentration will be, if the solution is acidic, we can expect that the hydrogen concentration will be greater than the hydroxide concentration, and that the hydrogen amount will be greater than our 1 times 10 to the negative 7th. We've already talked about those exponents that you're going to see like -6 or -5. These are showing higher amounts of hydrogen. If we flip it, if we start adding base to a solution, the solution is going to start becoming basic, and we're going to start to see a rise in hydroxide concentrations. Therefore, the hydrogen concentration will start to decrease. And the hydroxide concentration, once it becomes basic, will ultimately be greater than the hydrogen amount, and the hydrogen concentration will be greater than that neutral number of 1 times 10 to the negative 7th. So the relationship that we're seeing is that if we start having a very acidic solution, a rise in hydrogen concentration, our hydroxide concentration decreases. Or if we start to have a very basic solution, we start to see a decrease in our hydrogen amount. So we see that that is an inverse relationship. So I don't know about you, but all of these numbers raised to the negative exponent starts to be a lot. And so in order to make things a little easier to read, they came up with a logarithmic scale. So we're going to use that button, that log button on your calculator. So the pH scale is a logarithmic scale that measures the acidity of a substance. pH stands for the power of hydrogen, and it simply measures the concentration of hydrogen. The scale that we use to measure how basic something is called the POH scale. And so remember, bases typically have hydroxides in them, so they would focus on the concentration or how much you have of the hydroxide amount. So this brings us to our formulas, bringing everything together. So to calculate the pH, you would hit negative and then the log button, and then you would substitute in the amount of hydrogen you have. So H and pH directly relate. To calculate POH, you would take the negative log of the hydrogen concentration. And then when we add those two together, so the pH and the POH, which are like my favorite scales, those two add up to a nice number of 14. If we want to go back to those exponential numbers, if we want to calculate the hydrogen concentration, it would be 10 raised to the negative pH. And our hydroxide concentration would follow suit. It would be 10 raised to the negative POH. And we know that both of those concentrations will multiply to be 1 times 10 to the negative 14th. But the main connection I want you to see, and we'll get practice, is that the pH scale is related to H, and the POH scale is related to OH. So a little more to do about the pH scale. The pH scale ranges from 0 to 14. Half of 14 is 7. Anything with a pH less than 17 is classified as an acid. Anything greater than 7 is classified as a base. And if you're right in the middle, you are neutral. I remember this scale as the alphabet. We go A to B. So you'll be given all of the formulas we just wrote down, so hopefully you're not freaking out. There is this diamond shape that's in your notes. It's not given to you on a quiz, but it can be helpful in seeing how everything relates to each other. So I'm going to give you a chance to write these in. So let's say you're given a hydrogen concentration. You can either solve for the pH or you can solve for the OH. So if you want to calculate pH, you would do the negative log of that number, and then you would be in pH. If you wanted to go backwards, it's just the opposite. It's 10 raised to the negative pH. If you wanted to go H to OH, I rarely do that, but if you did, you just remember that your hydrogen and your hydroxide concentration will always equal 1 times 10 to the negative 14th, that equilibrium amount. But going back, if I calculated into my pH and POH are related to that those two things always add up to 14. If you notice, our connection between H and OH involves a 14 on both sides. And then lastly, POH to OH, very, very similar to pH and H. If we want to go into OH, you do the inverse. It's 10 raised to the negative POH. If you have a hydroxide concentration and you want to calculate POH, you do the negative log of OH. So let's do a problem. So here it says we've been given a hydrogen concentration of 5.5 times 10 to the negative 4th. And they want us to solve all of the following questions. So they've given us our hydrogen amount, 5.5 times 10 to the negative 4th. There are multiple ways to do this. My favorite is to go immediately to the pH or the POH scale. Like, I want to get out of these times 10 to the negative numbers. So because I'm in H, that directly relates to pH. So I'm going to calculate my pH first. And so following my formula, it says to take the negative log of the hydrogen concentration. So for this example, it will be negative log 5.5. I'm going to switch it to E negative 4. So literally in your calculator, you find the negative button under the 3, hit the log button, and then type in your concentration, 5.5 E negative 4. And if we calculate this, we get a concentration of 3.26. Oh, that 2 went crazy. And so right away, I'm like, man, I'm on the pH scale. I have something less than 7, and so I know this solution is acidic based on the pH. From here, I just want to stay in my simple numbers, so I'm going to go to POH. And so I have to remember that the relationship between POH and pH is that they add up to 14. So I know that my pH is 3.26. I'm looking for my POH. I know that it has to add up to 14, so opposite of addition is subtraction. So 14 minus 3.26 gives me a POH of 10.74. So then the last thing I have to do is find my OH concentration. I think at this point it's a little easier because we now know the POH. So it says if you want the OH concentration, it's 10 raised to the negative POH. So 10 to the negative, and my POH was 10.74. Now, unfortunately, we can't leave it like literally like this. Like you need to plug this into your calculator. So 10, use the caret, and then negative 10.74. And that will give you a concentration of 1.8 times 10 to the negative 11th. So we have lots of numbers going on. We were given the hydrogen concentration. We just solved for the hydroxide. We know the pH. We now know the POH. They ask, is this solution acidic or basic? This can be overwhelming with all these numbers. So for me to stay consistent, I always focus on the pH number because I know that pH scale the best is 0 to 14. I go A to B. So when my pH falls at 3.26, it falls in the acidic region. Okay, let's try another example. Change up the colors. This time they've given us a POH of 1.10 and they want us to solve for everything else. So, like I said, lots of different ways to do this. As long as you show your work, it doesn't matter the order. I personally love to hang out with pH and POH just because it's simple. And so 14 minus 1.10 it will give me a pH of 12.9. In my head, I was like, boom, that's basic. But we'll also check in at the end. And now I have to go back to my concentrations. Doesn't matter which one. I'm just going to start with OH. So using my formula, so you remember you are always given all of these formulas. So to calculate hydroxide, I need 10 raised to the negative POH. And so that will be 10 to the negative 1.10. Literally plug it in your calculator. Don't stop there. We can't have exponents with a decimal. And we get the value of 7.9 times 10 to the negative second. Now, some of y'all's calculators, it might have come out to be like 0.079. That's the same number. So either answer is correct. This just means it's really concentrated. This is a very basic solution if we have this much OH. And then lastly, we need to do our hydrogen concentration, which would be 10 to the negative pH, raised to the negative pH. So 10 raised to the negative 12.9. And once we plug that in our calculator, it's 1.3 times 10 to the negative 13th molarity. So to decide if it's acidic or basic, I personally just always look at the pH scale. And I'm going to draw it lots and lots of times so it sticks in your brain. And if we have a pH of 12, then that falls in the basic region. Okay, last little part, we're going to bring it all onto a chart. So you will often see it in this way. So you can make your own notes. I just remember pH and POH, they always add up to the 14. H and pH relate, OH and POH relate. So kind of like our first example, they've started us off with hydrogen. I immediately want to go to my pH scale. I just want to get out of those exponents. And so how do I calculate pH? We take the negative log of this number. So negative log of 2.5 times 10 to the negative 8th will give you a pH of 7.6. For me personally, I want to stay in those easy numbers, so I'm going to jump to the POH scale, and I'm going to do 14 minus 7.6 to get me a POH of 6.4. And then lastly, I need to solve for my OH concentration. I call it, we got to throw it back. And so I look at my formulas, and it will be 10 to the negative POH. And so we'll do 10 raised to the negative 6.4, plug it in your calculator, and you'll get 4.0 times 10 to the negative 7th molarity. Decide if this solution is acidic or basic. You can look at a lot of different numbers. Like I see that my hydroxide is a greater amount than my hydrogen, but if I stay consistent, my pH scale is above 7, which makes it a base. Okay, let's try row 2. This time they've started us off with pH, which I can already say is basic. It's greater than 7. And I'm just going to jump right over to POH. And so 14 minus that will be 2.5 because both pH and POH add up to 14. And then I call it, we got to throw them back. We got to put them into their exponents. And so this will be 10 raised to the negative pH. And then plug that in, and you'll get 3.2 times 10 to the negative 12th. And then same thing for OH, 10 raised to the negative POH. And so that will be 3.2 times 10 to the negative 3rd. Once again, you can see we have way more OH than H, and so that also confirms that we know it's basic. Last one, they started us in OH. OH directly relates to POH, so I call it knock it down. I want to get into those easier numbers, so I'm going to take the negative log of this number, and I get a POH of 10.92. From there, I can hop over to pH, because they're related they both have to add up to 14, so 14 minus 10.92 gives me a pH of 3.08, and then I've got to throw it back and get to my hydrogen, so that same pattern, 10 raised to the negative pH. If I remember correctly, the biggest thing y'all forget is the negatives, so just be mindful. You have the formula, you don't have to memorize it, it's 10 raised to the negative pH. And so once you compute that, it will be 8.3 times 10 to the negative 4th molarity. And then is this an acidic or basic solution? A lot of different ways. I'm going to go to the pH scale. We have a pH of 3, so anything less than 7 is an acid. That also is confirmed that we have way more hydrogen than hydroxide. So this concludes your 16B pH calculation lesson. Hope you guys are feeling like rock stars. If not, you can always re-watch the video, come in for help. Right now in class, you have time to practice, and we know that practice makes perfect. So please make sure you have your calculator out, you're staying on task, and I will see you guys next time.